Let's look at basic differentiation, where the definition of a derivative, so the derivative of f at x, that f prime of x says this is the derivative, is found by taking the limit of f of a plus h minus f of a all over h, and we're letting h approach 0. In other words, we're taking those secant lines and getting closer and closer and closer and closer and closer till we finally only touch that one line, which is our tangent line. And this is important, that this limit has to exist. And so with this, finding this limit is the definition of finding the derivative. And you'll see different notation for the derivative. You'll see y prime, you'll see f prime of x, or just f prime. Leibniz had his own notation. I kind of like it a little better, at least this first one, because it helps to see how to read the units. So in other words, this is like saying the change in y over the change in x. So the change in dollars over the change in days. I don't tend to use these others. I might use this dx, but I don't tend to use these as much. But again, this first one I do like a lot because it helps actually be able to read the units by looking at the numerator per the denominator. Some examples of seeing this written in this Leibniz notation is, let's say we have the cost C of a steak in dollars as a function of the weight W of the steak in pounds. So how you would see this written, the change in the cost over the change in pounds. So it would make sense that the cost of a steak would change if it's a function of the weight. So the change in cost over the change in pounds, with units dollars, because cost is in dollars per pound. The number n of gallons of gas left in a gas tank is a function of the distance d in the miles the car has been driven. So remember, a derivative's a rate, so that's what this is given, the change in gallons per change in miles. And so we get our change in gallons per mile. If we have a constant function and we use our limit definition, and I want to find the derivative of y equals 3 or f of x equals 3, well, I don't have an x here, so I just simply plug in my 3 minus 3 and I get 0, and I get my limit is 0, so the derivative is 0, which should make sense, because if I have the graph of y equals 3, then that's a horizontal line which would have the slope of 0. Remember that when you're finding the derivative, you're finding the slope, the rate of change, and the slope in this case would be 0. So the constant function rule says if you have any constant, okay, it doesn't have to be 3, it could be 15, it could be pi, it could be any constant, then the derivative of a constant is 0. So if we want to find the derivative of x cubed by using our definition, where I see an x, I plug in x plus h. Where I see an x, I plug in an x. I cube this piece out. So that's my cube formula. And then I go through here and I say, well, x cubed and minus x cubed cancel. And then I could factor out an h and cancel out some h's. I can let my h approach 0. And then I get my answer of 3x squared. So that's what we did. We did this definition, our derivative definition, to go through all these steps, taking the limit, to find the derivative. Well, now I'm going to tell you, you don't have to do all that. There's a shortcut. So the shortcut is this power rule that says all you have to do is, if you have a power like x cubed, bring the power down front. That's what this definition is saying. Bring the power down front and subtract 1 from the exponent. So in other words, you didn't have to go through all those steps. Bring 3 down front, and notice 3 minus 1 is 2. So this is a shortcut. This power rule instead of having to go through all of these steps. And I know you're thinking, well, why do you make me go through all those steps? Because my teacher made me go through all those steps, so you got to go through them too. You know, it's good to see the steps at first to understand what you're doing, but then of course it's kind of nice on some of these derivatives that if you can do the shortcut, you do them, but guess what? There will be times that you can't always use the shortcut rule, and so that's why you need to know the definition. Remember this one, the 16t squared, okay, where we had the object falling off the towers of America. We went through all these steps and wanted to know at exactly 1 second, okay, in this case, how fast the object was falling. Well, this is a power, so I could bring the 2 down. So 16 times 2 is 32, and subtract 1, and that gives me my derivative. Instead of going through all of those steps, in one step, I could simply do my power rule, bring this down, the 2, so I multiply it if there's something there, and then subtract 1. The sum and the difference property is nice when you have difficult functions, but a lot of times you'll just do these in one step. But basically what this is saying is if you have two functions and you're adding or subtracting them and you want to find their derivatives, you can find them individually and then add or subtract them. And this is just showing you different ways that you can write finding the derivatives. So we had this example here where we found the derivative of the square root of x plus 2. And how did we find the derivative? We went through all these steps. Okay, so we've done this already to be able to find this was the derivative for this function. Well, now we're going to find a way to do a shortcut. So I want to remind you, if you have a square root, that's the same thing as the 1/2 power. Okay, so I don't know if you remember that. It may have been a while, or you may have never seen that you can rewrite a square root to the 1/2 power. And so now I have a power here, so I can take the derivative of this piece, x to the 1/2, and I can take the derivative of 2. So the derivative of x to the 1/2, I bring the 1/2 down, and then I subtract 1. The derivative of 2 is a constant, so that just becomes 0. So all I'm working with is this piece right here. I just need to do 1/2 minus 1. Well, 1/2 minus 1, get a common denominator, 2 over 2. 1/2 minus 2 over 2 is negative 1/2. And so I get 1/2, and I bring the negative exponent to the denominator. Remember, if you have a negative exponent, you can move it to the denominator. And as mentioned before, the 1/2 power is the same as the square root. And so now, instead of going through that whole page of steps, all you have to do is make your square root a power, and then you can find your derivative very quickly with this shortcut. The constant multiple, so here's a constant, so 3 times x. To find the derivative, where we had an x, we plug in x plus h, then we plug in an x, and I multiplied all this out. The 3x's canceled, the h's canceled, and so I simply got 3. If you remember, we're just finding the slope. So I should be able to just look at that and I say, well, y equals mx plus b. So if your power is to the first power, then it would be this value would simply be your slope. Now the constant multiple property says you can take that constant and pull it out front here, and then all you have to do is take the derivative of x. So why is this x? Well, if I look at the derivative of x, remember that's x to the first power. We said the power rule says to bring the 1 down, subtract 1, so I get 1 times x to the 0. Well, anything to the 0 power is 1. Or this is just simply 1 because this is linear, and that's 1x there, and that would give you your slope, which is 1. Now, this constant multiple rule, in fact, you probably noticed when I did the 16t squared, the 16 had a constant in front. A lot of times students won't break the constant out front. They'll just multiply the power by whatever the constant is, and that's okay. You can certainly do that. There's nothing wrong with that. It's just sometimes you like to pull that constant out front if you have a very complicated function that you're dealing with. Okay, let's look at some examples here. Let me get a pen working. Let's just make some stuff up. So let's say I wanted to find the derivative of 4x cubed plus 3x squared minus 2x plus 7. And I wanted to do it with the shortcuts. I didn't want to put this big old thing in where I see an x, I have to put x plus h and all that good stuff, because this would be a long one, right? So the power rule says to bring the 3 down, and I can either throw the constant out front and multiply later, or I could just multiply now. So 3 times 4 would be 12, and then I subtract 1 from the exponent, so I'm going to have 12x squared, because I subtracted 1 from my exponent, and then plus 2 times 3 is going to be 6, and I'm left with just 6x because I subtract 1, minus my 2x is just going to be 2, and then my derivative of my constant is going to be 0. So that would be my answer. Well, what if I had the derivative of 1 over x squared? Well, I remember that I can rewrite when I have a power in the denominator, I can bring that to the top, but it becomes negative. So x to the negative 2 is the same thing as 1 over x squared. And now I can use my power rule that says bring the negative 2 down and then subtract 1. Well, if I'm subtracting 1, I'm actually adding 2 negatives, right? Because that's a negative and a negative. And I get negative 2x to the negative 3. And if you wanted, you could put it back in the form that you started with and move the exponent down to the bottom. Okay, so when you move the exponent down to the bottom, of course it becomes positive, and that would be your answer. Remember, the key here is the derivative gives you a function that you could then evaluate at a particular value of x or whatever your variable is. So a company's total sales in millions of dollars t months from now are given by S of t equals square root of t plus 2. So we did this last lecture. Find the derivative and then evaluate it at 25. So this is one way you might see it written, or this way, the change in sales over the change in time evaluated at time equals 25 months. So to do this, we found the derivative, which was 1 over 2 square roots of t. And then to evaluate it, you simply, where you see a t, you plug in 25 and you get your answer. If I have my 16t squared and I wanted to find f prime of 1, I find my derivative, which is 32t, and then I simply plug in 1. So the evaluating derivatives is just like you evaluate functions, because derivatives are functions. You find the derivative first, and then you plug in the actual value. Let's look at this advertising example. It says a marine manufacturer will sell N of X power boats. So this tells me how many power boats after spending X thousand on advertising. So X is the amount they're spending on advertising, where X is between 5 and 30. Well, what does that mean? Well, that means they have to stay between 5,000 and 30,000, because X is in 1,000, for advertising. I mean, that's just a restriction. That's just how much money they have to spend. find n prime of x, which says find the derivative of that, and then plug in 10 and tell me what it means. So this might be a good time to pause the video and you do it and then come back and see if you got the same answer I had. So I would play some pause music right now, but it's kind of early, so I'm not sure you want me to sing. Alright, so first thing I do is I change this like we did on some other ones where I bring the x to the top, and that becomes -1 because it's x to the first power. I bring it up top because now it becomes a power, which is nice. I find the derivative by the derivative of 1,000. That's a constant. That becomes 0. This derivative, I bring the -1 down, so a negative times a negative becomes positive. I subtract 1, and so I get -1 minus 1, which is -2. And then I just simply throw the negative exponent on the bottom to make it positive. So this is my derivative function. I plug in 10. So I put in 10 here, which is my advertising, my $10,000. And I leave this as a fraction because that helps me read. In other words, again, my change in the top over the change in the bottom. Well, remember what these meant is you can certainly see because we plugged an X in the bottom as that's my advertising. So this says at the 10,000 level of advertising, that came from that 10 plugging in, sales are increasing. Why are they increasing? Because my rate is positive at the rate of about 38 votes per 1,000, because that's 1,000 spent on advertising. So this part's very important that you understand how to interpret your answer. Otherwise, you go to your boss and you say 37.8. Well, 37.8 what? Do I need to spend 37.8 thousand in advertising? What do I need to do? And so this part's very important that you get the interpretation down as well as, of course, the math.